Okay, so at this point we understand how to do homogeneous transformations when there's only a translation involved, right? When we're not actually rotating the coordinate frame at all. And in this lecture, we're going to talk about what you have to do if there's actually a rotation as well. So just to review where we are to date, we've been talking about how to transform points between coordinate frames. So for example, maybe we have two coordinate frames here. We have the world coordinate frame, which has a W subscript, and we have the robot coordinate frame, which has an R subscript, and they happen to be perfectly aligned. The z-axis points in the same direction as the z-axis on both. The x-axis for world points in the same direction as the x-axis for robot. The y-axis for world points in the same direction as the y-axis for robot. And the only difference is that the origin of the world coordinate frame is 3 units to the left of the origin of the robot coordinate frame. And you can imagine that maybe we have a point located up here, and maybe I know the location of that point in world coordinates, and I want to find out, well, what's its location if I want to know it in robot coordinates? Or maybe I know the location of that point in robot coordinates, and I want to figure out, well, what's its location in world coordinates? So notice that the location of the point, the actual real location of the point, doesn't move. The point isn't moving, but it will have a different XYZ coordinate depending on whether the origin of your coordinate frame is here or the origin of your coordinate frame is here. And here's the key thing that you need to remember, and if you don't remember it, then go back and watch the previous video, right? There are two very important concepts. The first concept here is what I was talking about with that point. You have a point, say, in J coordinates, and you want to know what's the location of that point in K coordinates instead. Then we're going to talk about the homogeneous transformation from J to K, right? And this is a notation that lots of people use. And then there's the other concept here, which is, well, how did I transform the frame J so that it actually is lines up with the frame K? So how do I move frame J so it lines up with frame K, right? And that is what I'm calling the frame transformation, the F from J to K. How do we transform the frame J so that it lines up with frame K? So just to review what we said before, suppose that to do that frame transformation, to get from frame P to frame Q, we end up moving A units along P's x-axis, B units along P's y-axis, and C units along P's z-axis, right? Then we can easily compute the F transformation, the frame transformation from P to Q by putting in this unit matrix here, the 3 by 3 unit matrix. We're going to put 0, 0, 0, 1 across the bottom, and we're going to put in the A, the B, and the C that we got in here, the number of units we moved along each axis. We're putting them in there, okay? So now we have a matrix, right, a 4 by 4 matrix. And I'm going to call this matrix the frame transformation between P and Q. But the cool thing is that the F from P to Q is exactly the same as, that's supposed to be a giant equal sign, the transformation from Q to P. That is, we can use the same matrix we can use it if we know the Q coordinate location of an arbitrary point in space, and we want to turn it into P coordinates. All we need to do is take this matrix here and use that to multiply, pre-multiply the vector representing our point in q coordinates, pre-multiply it by this matrix. Just because I find students find this so hard to remember, I'm going to just tell you one more time, right? This T transformation from J to K is the transformation that takes a point, and it's a fixed point, right? And we know the location of that point in J coordinates, and it's going to compute the location of that point in K coordinates if you pre-multiply the point by this transformation. And again, this F thing is my personal notation that is also equal to the T thing. T from J to K equals F from K to J. And that's the easiest way to figure out the T matrix is first figure out how to move the other way with the frame. So how to move frame K so it actually aligns with frame J. So right now, we have no problem figuring out the F equation. Oops, that was circling with a white pen. That's not going to do very much. The F equation, if we only have a translation when we do that frame movement. But what happens when we want to actually do a rotation, when our frames aren't perfectly lined up, the z-axis lined up with the z-axis, x with x, and so on? So here's an example where there's no translation at all. It's just rotation, right? So if you look, we've got two coordinate frames here, J and K. Here's the xj, right? It says it right there. And let's see, yj is right there, and zj is there. And if you check, you'll see that that's actually a right-handed coordinate frame. But we've also got the K coordinate frame, where we have, through the magic of different colors of ink, we have xk points that way, yk points that way, and zk points that way. Now, you might find this easier to see if I show you the two coordinate frames separately, right? They're overlaid, right? So in reality, these two coordinate frames share the same origin, right? 0, 0, 0 is located in the same place. But in the J coordinate frame, x comes out of the screen, y goes to the right, and z goes up, whereas in the K coordinate frame, x goes to the right, y goes into the screen, and z still points up. But remember, these two pictures on the right here are just to get you, to make it easier for you to understand what this picture looks like. This is the real picture with the two frames having the same origin. So if we consider the origin of the j-axis, and remember I'm using this transpose notation because, I circled it in white, didn't I? This transpose notation because really our points are always vertical vectors, right? Then what's its location in K coordinates? Well, that one's easy, right? We say the location in K coordinates of the origin of the J axis. Well, that's located right there. Did you see that? Right here, right? So its location in K coordinates is exactly the same thing. It's 0, 0, 0. That's supposed to be 0, 1, right? It's exactly the same. So that was pretty easy. But now, what if we have the point A, B, C, 1, right? So 1 is the weighting factor again, in J coordinates, right? So A, B, C, 1 is the same as A, B, C, right? We have the point A, B, C in J coordinates. So remember, this is xj, there's yj, and there's zj. So maybe, we go A units out along the x-axis and B units along the y, and then we go up to this point by C, right? So let's color that in. So we went A along the x-axis and B along the y-axis and C along the z. Where do we end up if we're in the K coordinate frame, right? And we can eyeball this, right? We can look at this and say, well, let's see. If I want to look at the K coordinates, then I need to consider where's the xk. Well, let's see. So here's the x-axis, and we went over, let's see, we went over b because that's equivalent to the yj. So our point is going to be whatever the same as the y was. So that's going to be b. That's fine. And the y-axis for the k coordinate frame points in the opposite direction from the x-axis for the j frame, right? But it's along the same line. So we have to take whatever the x value is here, which in this case is a, and we went a units in that direction, which is the negative direction for y, so we need to say negative a. And then it looks like the two z-axes are in the same direction, the same location, so we can just copy that c there. So our new point, if we want to do it in our matrix, in our vector notation, we would say that's b, negative a, c, and 1 as our weighting factor. Now, something interesting to note on this frame, as I said before, is the z-axes are perfectly aligned, right? If you look, the zk axis is the same as the zj axis, right? And also remember, our origin is the same. So you can kind of think of this, if I'm trying to go from j to k coordinates, I can sort of imagine that I'm going to spin my frame about the z-axis. So if you kind of imagine I'm just grabbing this axis by the top here and spinning it, I can turn j coordinates into k coordinates, right? Because if I spin it, and it looks like if I spin it by 90 degrees, right, this way, then after I'm done the spinning, my x-axis, which used to be pointing in this direction, if you spin by 90 degrees, I grab right here, right, and I spin, you can see that the new x-axis is going to be that way. And similarly, if I started with the y-axis pointing to the right, after that spin, the y-axis is going to be pointing into the screen. But the z-axis, since that's the one I'm spinning, sort of stays put. It's, you know, infinitely thin, so it stays put. On the other hand, if I'm trying to move from k coordinates to j coordinates, right, I want to transform my frame from k coordinates to j coordinates, then I got to spin the other way. And remember your right-hand rule for figuring out the direction of spin, right? If we point our thumb along the z-axis, then the positive direction of spin is this way. But we don't want to do that now. If I'm trying to go from the k frame to the j frame, then I need to spin this way. So that's a spin of negative 90 degrees, right? So I'm actually rotating about the z-axis by negative 90 degrees. And again, you can see that that works. If I grab right here and spin by negative 90 degrees, then after I'm done the spin, this y-axis, which used to be the k-axis, will be pointing off to the right, right? Because it spins, right? And the old x-axis for the k coordinate frame will go over to here, so it'll be lined up with the j-axis. So we've said that if we want to do a frame transformation from k to j, that's essentially doing a rotation about the z-axis, about taking k, grabbing it by its z-axis, and rotating it by negative 90 degrees, right? And I'm just going to tell you that the equation for rotate z by theta is actually this 4x4 matrix, okay? Fine. So if we know that this is rotate z by theta, and I'm trying to rotate from k to j, and or I'm trying to figure out the frame transformation from k to j, and that is rotate z by negative 90, then we just got to substitute the values for cosine and sine appropriately, and we win. So let's do it. And I'm assuming at this point that you remember your sines and cosines, right? So, I like to think about the unit circle when I'm trying to remember my sines and cosines. So just to review, here's my unit circle, and I draw that horizontal line there. And if I want to know if this angle is theta, then this vertical line is going to be my sine of theta, and this horizontal line under here, this little piece, is going to be my cosine. So in this particular case, I've rotated by negative 90 degrees. So here's where I am at. So let's see, my cosine of negative 90 degrees is actually 0, right? The sine of negative 90 degrees is going to be negative 1, but I need to take the negative sign here, so I'm going to end up with 1, and then 0, 0. For the next line, again, we need to know the sine of negative 90 degrees, so now we have a negative 1 there. Cosine of negative 90 degrees is 0, and then we have another 0, 0. Next line, we've got 0, 0, 1, 0, and finally we have our 0, 0, 0, 1. Okay? So we end up with this matrix for our frame transformation from K to J, and this matrix also equals rotate Z by negative 90. So here's a nice clean version of that matrix. And now let's do a sanity check. Let's see if this at least works for the examples that we tried before. So here is our frame transformation matrix, right? And we know that the origins of these 2 points are identical. And we also remember that this computation was f's from K to J, and that is actually equal to is equal to T. That looks like a T, right? That's equal to T from J to K. So if here I've got my T from J to K, if I assume this point is in J coordinates and multiply them together, then I should find out the location of that in K coordinates. And if you do your matrix multiplication, let's see, the first row, oops, sorry, it's going to be a vector again. I don't need that much space. First row is 0. The second row is 0. Look at that. The third row is, oh my goodness, 0. And the last row is 1. So actually, this one worked. But of course, that was at the origin, so who knows? Let's try our arbitrary point. So we claimed that this point in J coordinates is equal to this point in K coordinates. And so let's see what happens if we have the f from J to K. That means we also have the T from, we have the f from K to J. That also means we have the T from J to K, right? So let's see if we can transform a point in J coordinates and see if we get the point in K coordinates. So let's say that we have the point A, B, C in J coordinates, and we want to multiply it by this matrix, right? And what do we get for the answer? Well, we've got a vector, right? In the first row, we have 0 plus 1 times B plus 0 plus 0, so we end up with B. Second row, negative 1 times A, and then all the rest are zeros, so that's negative A. Third row, 0 plus 0 plus, C, 1 times C, right, plus 0, so that's C, and the last row, 0, 0, 0, 1, so that just gives us a 1. And check it out. That is, in fact, the same as the point in K coordinates that we computed just by eyeballing it, which is really pretty cool. So where are we? Well, we can now compute the F and therefore the T matrix when the two frames only differ by some sort of a translation, right? Along some combination of, we can translate along X, Y, and Z axes, and we're all right. And we can also compute the F matrix, which gives us the T, of course. If we just have a rotation about the Z axis and nothing else. And now we're going to go on to the general case. What happens if you have a bunch of rotations and translations about arbitrary axes? How do you compute that? Well, it turns out there are two different ways to do this. One way is using the moving axis approach, and the second way is using the fixed axis approach. And both ways of computing this do give you exactly the same answer. And you should learn how to do both, because occasionally some problems are easier to solve with one approach than the other. Typically, students find the moving axis approach a little bit more intuitive, so we're going to do that first. But if you're in my class, you need to be able to do both, because I'm going to ask you to do both. So here's the first question. We have two coordinate frames that are 5 units apart. So there's a translation of 5 units, but if I make this thing a bit bigger, you'll see that that the axes also have some rotations, right? So you can see that, let's call them world and gripper coordinates. The axes are pointing in different directions, right? So for example, the x coordinate in world coordinates is pointing this way, whereas the x in gripper coordinates is pointing up, right? So x world is, what way is that? That's out of the paper, right? Out of the screen towards us. So the first thing I want you to do is just try and figure out, how do you do a transformation between these two frames? And in particular, I want you to compute the frame transformation from W to G. So I recommend you stop this video and you grab 2 physical things that you can play with. I like Tinker Toys, but something that you can set up worth 6 pencils in pairs of 3 that you have taped together or something, so that you can try and figure out, how do I start with world coordinates and do the rotations and the translations so I end up with gripper coordinates. And of course, there's a bunch of ways to do this, right? We could do the translation first and then some rotations, or the rotation and then some translations. But what I want you to do is just figure it out on your own, and then I'll show you my approach. So here's my way to do it using a moving axis approach. I'm going to start by considering what world coordinates look like. And just for your reference, I've put a copy of both coordinates frames up there so you can see. And the first thing I'm going to do is I'm going to rotate about the world's x-axis by -90 degrees. And I'm going to call the resulting coordinate frame, frame 1, right? And I'll call its individual axes x1, y1, and z1, just so we can see what's going on. If you use your right-hand rule to figure out which way is positive rotation, you'll see that we want to rotate about the x w axis sort of in this direction, right? Because I said I want to do -90 degrees, so I need to do a negative rotation, right? And that's going to bring the z-axis down, the y-axis, the z-axis is going to end up pointing to the right, the y-axis is going to end up pointing down. But remember, we're grabbing it here to do that rotation, so the x-axis is just going to stay where it was. And here's a sort of before and after, right? So now you can see both the world coordinate frame, which I've labeled with W subscripts, and also the frame 1, right, which is after I've done that rotation. And in here I've drawn frame 1 in yellow, and the original coordinate frames are in blue, black, something. So here's coordinate frame 1 by itself. And now what I'm going to do is my next move is I want to rotate about the z1 axis by -90 degrees. So a positive rotation around the z-axis would be sort of in this direction. But I don't want to do a positive rotation. I want to do a rotation around the z-axis by -90, so I'm going to go like that. So again, I'm grabbing this and spinning it like that. So when I spin that, what happens? Well, the z-axis isn't going to move, right? I'm grabbing onto that and holding it. But x, when I spin it round by 90 degrees, is going to end up pointing straight up. And y, when I spin it round by 90 degrees, is going to end up pointing out of the page towards us, the way x was pointing before. So here's that picture again. You can see that I've now colored our x2 axis in the blue again, right? So x1 is where we were, and then we did that rotation, and we ended up with x2, y2, z2. So now if you take a look, our frame 2 is actually, the axes are lined up with the axes of my gripper coordinate frame, right? X points up, z points to the right, and y points out of the page. But we still have this issue of the distance between the two frames, right? We need to translate, we need to somehow move 5 over. And how are we moving? Well, we're going to move relative to coordinate frame 2, and we need to move 5 in this direction, so that's positive z, so that would give us 0, 0, 5 is what we're moving, right? Because x, y, z, x is 0, y is 0, but we are translating by 5 along the z-axis. Whose z-axis? Well, the z-axis of frame 2. And after we do that move, we end up with our final coordinate frame gripper coordinates that are over here. So let's just review what we did. We rotated first by negative 90 degrees about the x world axis. Then we rotated about the new coordinate frame, the coordinate frame 1 z-axis by negative 90. And then we translated by 0, 0, 5, and that was all relative to coordinate frame 2. And the really important thing that you need to note here for moving axes is every step along the way is based on the resulting frame from the previous step. So when we did that rotation, our second rotation, about the z-axis by negative 90 degrees, that was about frame 1's axis, not on the world axis, right? And so here's a list of our moves that we did. The first thing we did was we rotated about the x-axis, that was the world's x-axis, by negative 90 degrees. And that kind of gave us, that put us into frame 1, right? And then we rotated about frame 1's z-axis by negative 90 degrees. And then finally, that gave us frame 2, right? And then finally we took frame 2 and we translated 0 along x, 0 along y, but 5 along frame 2's z-axis, and that gave us our final gripper coordinates. Now, eventually what we're going to do is we are going to just take each of these moves and turn them into a 4x4 matrix and multiply those matrices together, and bing, bang, boom, we will have our result, our resulting F matrix, right? Remember, we were trying to figure out our F from W to G, which is going to be the same as T from G to W. And we'll do that substitution in a minute. But for now, I just want to talk to you about the other approach. So we use the moving axis approach. And the key thing to remember about the moving axis approach is that every step along the way, this is supposed to look like highlighter. I don't think it's doing a great job. Every step along the way is based on the resulting frame from the previous step, right? Let's just try using a pen instead. It's fun, this tool. Every step along the way is based on the resulting frame from the previous step. We're moving along, right? That's the moving axis notes. In contrast, when you use fixed axes, every move is going to be relative to your start coordinate frame's axis. In this case, it's going to be the world coordinate frame, right? So every single thing that we do always is in terms of x is pointing this way, y is pointing this way, and z is pointing that way. So let me talk you through this. Here's going to be my approach. The first thing I'm going to say is let's rotate about the x world axis by negative 90 degrees. So again, negative 90 degrees is pointing in that direction, right? So here's my prettier arrow. And after we do that rotation, we end up with this sort of yellow or orangey frame, right? We have frame 1 coordinates, right? But I've left world coordinates in blue on this page because they're still very important. So our next step is going to be to do this rotation that I've shown here, right? It's going to be a rotation kind of like that about this axis. And the issue is that we need to agree on what we're going to call that axis. And I said that since we're using a fixed axis approach to this problem, everything is going to be about the world coordinate frame. So we're going to do this rotation about this z-axis. Excuse me. But actually it's about frame 1 z-axis, but it's about the y coordinate frame if we're talking in world coordinates. So, and again, that's a negative 90 degrees if we're looking at the y-axis. So we're going to rotate about y world because every rotation we're talking about is still in world coordinates. So I've tried to show you everything that's going on here, and I don't know if it's completely clear. I've left the coordinate frame 1 in here in sort of the orange. Coordinate frame 2 actually lies entirely on world coordinates. It's just that if you look here, x2 is the same as the z world coordinate frame, right? And z2 is the same as the y world coordinate frame. y2 is the same as the x world coordinate frame. So everything is lined up, and if you look, we've now got to the same point that we were at before, where in our previous example, where frame 2 is actually, the orientation of frame 2 is the same as the orientation of gripper coordinates, but we still need to do that translation. Because right now, frame 2 is located here, and we need to move it over to here in order to get into gripper coordinates. So what do we need to do? Well, we need to translate 5 units in this direction. And again, we do it relative to the world coordinate frame, so that's 5 units in the y-axis, which is 0, 5, 0. So here's all those moves, right? We first did the rotate. Whoops, sorry. We first did the rotate, then we did the we first did the rotate about x world, then we did another rotate about y world, and finally we did a translate relative to world coordinates, so we were moving in the y direction according to world coordinates. Now, the key thing to remember about the fixed axis approach is that every move is relative to your initial frame. So here's the moves we did. We did rotate x by negative 90, rotate y by negative 90, and then this translate. So again, a lot of people mix these things up. It's really important to understand what's moving coordinates, what's fixed coordinates. In moving coordinate approach, each move is relative to the frame that resulted from the previous one. In the fixed approach, each move is done relative to the original frame, right? And so if you look, we started out in both cases with a rotate x by negative 90, but after that, even though we did, I think, the same sequence of moves, right? The rotations, the actual rotations that we were doing looked the same, because in moving coordinates we were relative to our new frame, and in fixed coordinates we were always relative to the original frame. The list of movements looks different. And notice again that our last step in the moving coordinate frame, we said translate 0 in the x direction, 0 in the y direction, and 5 in the z direction. In fixed coordinates, it was 5 in the y direction and 0 in the other two. And so as I hinted at before, the way we're going to get to the matrix is we're going to multiply a bunch of 4x4 matrices. For the purposes of my class, you don't have to memorize this, and you'll find it in the reading, but you really need to become comfortable using these things. So here are the 4 sets of equations. This tells you if you want to do a translation of A along the x-axis, B along the y-axis, and C along the z-axis, you fill in your values here. If you want to do a rotation about the y-axis of theta degrees, you use that matrix. Rotation about the x-axis of theta degrees, you use this matrix. Rotate about the z-axis of theta degrees, you use this matrix. If you're using the moving axis approach, then the first step of what you need to do is you need to list the moves you made from left to right. So I've put the moves right here that we made, and the first step that we need to do is just list them from left to right. So there you go. First thing we did was rotate x -90, so we put that on the left. Next was rotate z -90, we put that next. Next was the translate, we put that there. After you've listed your moves from left to right, then you need to replace each move that you have with the appropriate matrix from that page of 4 different matrices on the previous slide. So, for example, rotate x by -90 turns into this matrix. Rotate z by -90 is this one, and translate 0, 0, 5 turns out to be this. And finally, the last step is you just multiply all your matrices together. So I'm not going to do this out by hand. Here's your result. So in contrast, when we're using the fixed axis approach, we want to list our moves from right to left. That's the only thing you need to do different. So here's our fixed axis summary. The first thing we did was a rotation, second thing was another rotation, third thing was a translation. But when we list them, we put our first rotation here, second rotation here, and then our translation. And then again, we're going to replace each move with the appropriate matrix. So instead of trans 0, 5, 0, we get that. Rotate y -90 and rotate x -90. And then we just need to multiply the matrices together. And when you do that, you get this matrix. And if you rewind, you will see that's exactly the same matrix that we got when we used the moving axis approach. So reassuringly, both ways gave us the same result. Now, before I explain to you how to do the same thing using the fixed axis approach, I want to give you a very important warning about rotations in the fixed axis approach. So far, we did all our rotations at first, and so the origin of the world coordinate frame, or the origin of our starting coordinate frame, was exactly the same as the origin of our sort of working intermediate stage frame. But when you get to an example like this, things can be a little bit trickier. So let's suppose that we started with G coordinates this time, right? So here's my G coordinate frame. And let's suppose we did a whole bunch of rotations and translations, and we're doing it using the fixed axis approach. So every time we do something, we do it relative to this frame, right? And at some point, we end up, after a sequence of rotations, and translations, we end up with this new frame, right, which I've called Z sub W. Maybe I would have been better to call it, Z sub 5 or something, because it's after the 5th step, but it's fine. And now what I want to do is I want to do a rotation. I want to rotate this frame. It says the W axis, but let's say the W frame by -90 degrees about the Y, this guy here, right? 90 degrees about that axis. So if we want to So just imagine that if we're rotating about the y-axis, right, this axis, sort of imagine that this axis is sticking out and everything else is sort of stuck together. Imagine you sort of are locking this frame into this one. If you do that, then when you do this rotation, you can imagine if these guys are fixed one to the other, then when you do this rotation about this axis, this isn't going to rotate around here. It's actually sort of connected and it's going to move up like that, right? So just imagine again that this is all connected somehow, right? So when I spin this guy, this is moving around the outside. And look at what the result is when we do that. Not only do we do a rotation about this in-out axis, right? And so we do end up rotating about this x-axis in some sense too, right? Because the z that used to be pointing up is now pointing to the right. The y that used to be pointing to the right is now pointing down, right? And the orientation of the x-axis hasn't changed. But sort of the scary thing is not only that, but the origin of our axis has moved, right? The origin of our axis used to be there, and now it's there. And that has never happened to us before when we do a rotation, right? And it's only happening because this coordinate frame we're not rotating about this coordinate frame's origin anymore. We're rotating about somebody else's origin. So when you're using fixed axes, be super careful if you have a rotation. And so just to summarize, when we're using moving axes, we need to remember to list the equations from left to right. When we're doing fixed axes, make sure you list the equations from right to left, and also be very careful when you're doing fixed axes about rotations if the origin of your intermediate step is not the same as the origin that you started with.